Welcome everyone. In this session, we will build a foundation for understanding machine learning and its applications in pavement engineering. Machine learning has become one of the most influential technologies in engineering, science, healthcare, finance, and many other fields. As engineers, our goal is not to become computer scientists, but to understand how machine learning can help us solve complex engineering problems more effectively. By the end of this lecture, you will understand the major categories of machine learning, common algorithms, and how these techniques can be applied to transportation infrastructure. This slide provides a high-level overview of the machine learning landscape. Artificial intelligence, or AI, is the broadest concept. Machine learning is a subset of AI that focuses on learning patterns from data. Within machine learning, we generally distinguish between supervised learning and unsupervised learning. In supervised learning, we have both inputs and known outputs. Examples include predicting carbonation depths, rotting, or moisture susceptibility. In unsupervised learning, we only have inputs and attempt to discover hidden patterns within the data. Examples include clustering pavement sections based on similar characteristics. Most of the applications we will discuss throughout this workshop fall within supervised learning. There is often confusion regarding the relationship between AI, machine learning, deep learning, and generative AI. Think of these concepts as nested circles. Artificial intelligence is the broadest category. Machine learning is a subset of AI that learns from data. Deep learning is a subset of machine learning that uses neural networks with multiple layers. Generative AI is a specialized area that focuses on creating new content, such as text, images, audio, video, or computer code. For pavement engineering applications, traditional machine learning methods such as random forest, XGBoost, support vector meshes, and neural networks are still the most common approaches. This slide summarizes the major differences among AI, machine learning, deep learning, and Gen AI. Notice how the amount of required data generally increases as we move from machine learning toward deep learning. Also notice that interpretability often decreases. Traditional machine learning models are often easier to explain than deep neural networks. As engineers, interpretability is important because we need to justify our decisions and understand why a model makes a prediction. This slide illustrates one of the most fundamental concepts in machine learning. In traditional programming, inputs plus rules produce outputs. Engineers explicitly define the rules. In machine learning, inputs plus outputs are used to learn the rules automatically. The algorithm discovers relationships directly from data. For example, instead of manually creating equations to predict pavement deterioration, we provide historical pavement data and allow the algorithm to learn the relationship between traffic, climate, material properties, and performance. So here we learn the typical machine learning workflow. First, we collect data. This data could be on anything that is relevant to the project. It could be data on material properties, traffic, climate conditions, so on and so forth. Second, we clean and prepare the data. So we try to transfer this raw data into a good quality data that can be used to train the model. In the next step, we train the model. So this is where basically we decide about the model and the algorithm that we would like to use based on the project, and basically using the data prepared in the previous step, we train the model that can perform the job for us. In the first step, we evaluate the model that was trained in the previous step. So basically, after training the model, now it's time for evaluating the model, and to make sure that the developed model is reliable and accurate. And finally, we use the model to make predictions. One important observation is that model training is only one part of the process. In practice, data preparation often requires significantly more effort than model development itself. So here we learn about the three major categories of machine learning. Supervised learning is used when labeled data are available, and examples include like regression and classification. Unsupervised learning is used when labels are not available and patterns must be discovered. Some examples include clustering, dimensionality reduction, so on and so forth. Reinforcement learning is used when an agent learns through trial and error by interacting with an environment. In transportation engineering, supervised learning dominates most applications because we usually have historical data and historical observations that can be used for training. In supervised learning, the algorithm learns a mapping between inputs and outputs. For example, inputs could be information on many different features like traffic, pavement age, binder content, airword content, anything related to the material properties, traffic condition, weather conditions, so on and so forth. An output could be variables related to the performance. It could be watt depths, it could be like international roughness index, fatigue related parameters, moisture susceptibility parameters, so on and so forth. The objective is to learn a function that can accurately predict outputs for new unseen observations. In other words, so basically we train a model and we build a model, and this model can help us to identify the output or predict the output based on some input values. This is similar to how students learn from solved examples before attempting new problems independently. Supervised learning can be divided into two major categories: regression and classification. Regression predicts continuous numerical values. Examples include like carbonation depths of cementitious materials or concrete, watt depths, international roughness index, dynamic modulus, and tensile strength ratio, so on and so forth. So all these variables are continuous numerical values. Classification includes predicting categories, so different categories of items. For example, moisture susceptible versus non-moisture susceptible, pass versus fail, good versus poor pavement conditions. So these are two different categories, or multiple different categories. So these categories represent the majority of engineering machine learning applications. So this slide provides an example on regression with further details. Suppose we would like to learn about the performance of a concrete mixture, And this performance could be performance related to different things like carbonation depths, modulus of elasticity of concrete, compressive strength of concrete, so on and so forth. And based on engineering knowledge, we know that the performance of the concrete mixtures that is kind of related to some input variables. We have an input set, we have some inputs and features such as water to cement ratio, fly ash content, exposure time, CO2 concentration. And we know that all these variables somehow affect the performance of concrete, affect the carbonation depths of concrete. But understanding the highly nonlinear behavior and how these variables interact is somehow difficult for us. So machine learning algorithm can help us to understand these interactions and can help us to build a model that relates all these input variables to the output variables. So there are many examples of regression algorithms that can be used. They come with different assumptions and different advantages, different limitations. So depending on the project that you work with on, basically you can select. You have a wide variety of options to select from. It can start from the very basic one like a linear regression, and it can move to some advanced ones like decision trees, random forest, XGBoost, support vector regression, artificial neural networks, so on and so forth. So this is just one example on concrete mixture. You can kind of expand this example to other projects as well. For example, suppose that you would like to estimate the tensile strength ratio of asphalt mixture, and you know that tensile strength ratio could be related to many input variables like airward content, binder content, nominal maximum aggregate size, so on and so forth. And you basically ask machine learning to find the relationship between the input variables and the output variable. Classification problems involve predicting categories rather than numerical values. For example, we may wish to classify asphalt mixtures as moisture susceptible or non-moisture susceptible. Instead of just focusing on the actual TSR value, we focus on the categories, and we know that there is a threshold of like 80%. So above 80%, that is kind of non-susceptible. Below 80%, that is kind of susceptible, moisture susceptible mixture. So the algorithm learns decision boundaries that separate different classes. Common classification algorithms include logistic regression, decision trees, random forest, support vector meshes, k-nearest neighbors, so on and so forth. So classification is extremely common in infrastructure management because many decisions ultimately involve categorical outcomes. Unlike supervised learning, unsupervised learning does not have known outputs. So remember in previous slides we had labeled data. We had a set of data on input variables like information on water to binder ratio, information on fly ash content, binder content, so on and so forth. We also had information on output variables like carbonation depths, like dynamic modulus, so on and so forth. But here in unsupervised learning, we don't have such information. The objective is to discover hidden patterns within the data. The algorithm attempts to identify structures, relationships, or groups that may not be immediately obvious. Think of it as exploring a dataset without knowing the answers beforehand. So, typical applications of unsupervised learning include, for example, customer segmentation, data exploration, anomaly detection, so on and so forth. One of the most common unsupervised learning techniques is clustering. Suppose we have hundreds of payment sections. Rather than analyzing each section individually, clustering can automatically group sections with similar characteristics. Potential grouping variables include traffic, climate, roughness, structural condition. These clusters can help agencies prioritize maintenance strategies or identify common deterioration mechanisms. This slide summarizes the differences between supervised and unsupervised learning. In supervised learning, we use labeled data. We have known output variables, for example, carbonation depth, for example, tensile strength ratio. And we focus on prediction. So the goal is to predict an output variable. In unsupervised learning, we deal with unlabeled data, and basically there is no labeled data in the system. And also there is no output, there is no target variable. Here we focus on pattern discovery. So basically the objective is to find hidden structures or groupings or relationships in the data. A simple rule of thumb is, if you know the answer during training, it is supervised learning. If you don't know the answer and want the algorithm to find patterns, it is unsupervised learning. Here we learn about some popular algorithms we will explore during this workshop. Some example of supervised learning include linear regression, decision tree, random forest, support vector machine, artificial neural network, XGBoost. In terms of unsupervised learning, for example, we will learn about k-means clustering, and PCA, principal component analysis, is another unsupervised learning. So basically each algorithm has strengths and weaknesses, and they also come with some assumptions. So there is no universally based algorithm for every project. The best model depends on dataset size, data quality, complexity of relationships, interpretability requirements, so on and so forth. So part of being a good engineer is knowing when to use each tool. There are several common misconceptions about machine learning. First, machine learning is not magic. It cannot create information that does not exist within the data. So basically it creates information using the data that you provide to the system. Second, more complex models are not always better. Sometimes a simple model outperforms a sophisticated model. Third, machine learning does not replace engineering judgment. Engineering knowledge remains essential for selecting variables, interpreting results, and validating predictions. The most successful applications combine machine learning with engineering expertise. So let's summarize the major concepts from this lecture. Machine learning is a subset of artificial intelligence that learns patterns from data. The two primary categories are supervised learning and unsupervised learning. Supervised learning includes regression and classification. Machine learning is a powerful tool for solving complex engineering problems, but success depends on high quality data, appropriate model selection, and sound engineering judgment. As we move forward in this workshop, we will begin applying these concepts using real engineering datasets and practical examples. The goal is not only to understand the algorithms, but also to understand how to use them effectively to make better engineering decisions.